In this video, we're going to discuss a right-tailed hypothesis test for the population mean. So this is different than in previous videos because this is a test for a population mean. But you'll notice that this type of hypothesis test, it's very similar to the test for population proportion with a few minor differences. Okay, so let's go ahead and read through the example. The researcher claims that the average number of hours that college students spend studying is more than 20 hours per week. A random sample of 36 college students found the average number of study hours was 23 hours. Assume that the population standard deviation is 8 hours. Test the researcher's claim using a 5% significance level. Right? So let's see, what are we going to be testing? We're testing that the average number of hours that college students spend studying is more than 20 hours per week, right? So let me go ahead and define mu to be the population average number of hours college students study, okay? All right, so we're trying to test if mu, the population mean, is more than 20 hours. That's the claim, that the population mean is more than 20 hours. So the first step, finding our null and alternative hypothesis. So now we're trying to test if mu is more than 20 hours. So the null hypothesis will be that we'll assume mu equals 20. Okay. So mu is greater than 20. That's what makes this a right-tailed test. We're going to be interested in values of our test statistic that are large, right? Because we have this greater than sign. So for large values of the test statistic, it's just a right side test, right-tailed test. All right. So the second step, after you've come up with your null and alternative hypothesis, is to come up with your test statistic. So the equation for our test statistic has changed a little bit. So it used to be, we had an equation for a test statistic for the population proportion. Now we're going to talk about a test statistic for the population mean. Okay, so the value of the test statistic is x bar minus mu divided by sigma over the square root of n. Now there's some requirements that you need in order to be able to use this test statistic. All right, so in order to use this test statistic, your data must be normally distributed. So data must be normal, okay, or n needs to be greater than 30, right? So if n is larger than 30, then you have the central limit theorem, which says that x bar is normally distributed. So x bar is normal. So you don't need the data to be normal. Okay. Another requirement is that sigma must be known. All right. So in the question, it'll tell us something about sigma. In this question, you see it says assume that the population standard deviation is 8 hours. So because it gave the population standard deviation, we were given sigma, right? Sigma is the population standard deviation, so it's given here in this question. Now, if n is very large, sometimes you can use the sample standard deviation to approximate the population standard deviation. So if n is large, then you can use the sample standard deviation to approximate the population standard deviation, and then you can go ahead and use this equation. Okay, so even if sigma is not given, if n is large, then you can go ahead and make this approximation to the population standard deviation, given the sample standard deviation. All right, so anyway, let's go ahead and calculate this guy. X bar in our problem says that in the sample of 36 college students, they slept on average 23 hours. So that's the sample mean. Okay, mu, that comes from the null hypothesis, so that's 20. sigma, the population standard deviation, is given in the problem to be 8 hours. Okay, so if we read that, assume that the population standard deviation is 8 hours. And then n is 36, because they randomly sampled 36 college students. Okay, so n is 36. So our test statistic is x bar 23 minus 20 divided by 8 over the square root of 36. So that's 3 divided by 8 over 6. Okay, so that equals 2.25. All right, so now third step is to calculate the p-value or to calculate the critical values. All right, I'm going to start with p-value. You really only need to do one or the other. I recommend doing p-values. So let's talk about p-values. All right, so start with thinking about your distribution of the test statistic given HO is true. Okay, so here we go. In the center we have 0. Our value of the test statistic is 2.25, and we're concerned with values of the test statistic that are very large because we're concerned with whether mu is greater than 20. So we're concerned if we have large values of the test statistic. So that's the right tail over here to the right of 2.25. So the p-value is the area to the right of 2.25. Right? If we go into our table, we're going to discover the area to the left. So I'll have to do 1 minus whatever the table will give me. All right, so let's look up 2.25 in the table. So 2.25. Okay. So 2.2, and then over to 5, 2.25. All right, so we get 0.9878. So 0.9878. That's the area here. So we want the area that I've marked here in green. So I have to do 1 minus 0.9878, which is 0.0122. All right. Okay. Now what is my alpha? What am I comparing this to? In the question, they told us alpha 5% significance level. So that means alpha equals 0.05. Right? So if this area is less than 0.05, I'm going to reject the null hypothesis. And turns out that in this case, yes, the p-value is less than my significance level. So this area, it's too small to be coming from, it's too small for it to be likely that the null hypothesis is true. So I'm going to be rejecting the null hypothesis given this p-value. All right, let's talk briefly about critical values here. All right, so say I decided to use critical values versus using a p-value. How would I go about and do that? Remember, you only do one or the other. You don't need to do both. All right, but if you do critical values, we'll think about the distribution of our test statistic given the null hypothesis is true. All right, so we center here, and then since it's a right-tail test, my cutoff for the critical value cutoff will be over here to the right of 0, and the area over here is alpha, which is 0.05. Okay, so my z critical value has the area to the right of 0.05, so the area to the left then would be 0.95. So if I go inside my table and I look for where 0.95 is, let's go ahead and do that. 0.95, okay, it's 1.645. So the z value is 1.645. All right, so any observed z values that are beyond 1.65 are considered to be in the rejection region, right? So this is my critical value for which if I observe any test statistic that's beyond in this region I've marked here as green, then I'll reject the null hypothesis. So let's see, what was our value of our test statistic? 2.25, right? 2.25. So that is in this rejection region, 2.25. So my decision is going to be reject the null hypothesis, right? So whether or not I use the critical value or the p-value, I get the same conclusion. All right, so step 4, go ahead and state your conclusion. All right, let's do this. So we know that we are going to reject the null hypothesis. Now, let's remember, what is our null hypothesis? That mu equals 20, and the alternative is that mu is greater than 20. So since we've rejected the null hypothesis, there's evidence to support the alternative. Okay, so we'll say that there is evidence to support that the average number of study hours is more than 20.